want to talk about some problems there from 7.2 dealing with the volume utilizing the disk method. But let's first recap on a problem or two from section 7.1. It's the 8th edition of the book, so each edition's the problem somewhat changed. It's kind of like the same problem, it may just change a number here and there. In 7.1 you were concerned about finding the area, and this information here was given. Well, the first thing we need to do is graph. Well, understand that if I have this is y equal to x, if I have the line y equal to x, something like that. Then if I have the line y equal to 2 minus x, the slope is negative, so it's going down, doing something like that. And at the origin we get 0. I need to find this point here, and the region that we're looking for is the bounded region.
Be everything in here. So to find this point, we set the two graphs equal. Notice that the line y equal to x is this guy. That's this guy right here. And the line y equal to 2 minus x is this line. And the line y equals 0 is here. So we have a bounded region, and we solve now for the values for x and which we want to integrate. You know, this is the line y equal to 0. So we set the two equations equal. So we have y equal to x and y equal to 2 minus x. So this implies then that x is equal to 2 minus x. We get 2x is equal to 2. So here x is equal to 1. Well, the x equal to 1, by the way, just so happens to be where. And so here this is x equal to 1, and if x is 1, then y is equal to 1 as well. Because you have y equal to x. Now, to find this point, let me get back to this guy. Simply, you know that y equal to 0, and so that implies that 2 minus x equal to 2. So my integration will go from x equals 0 to x equal to 2. And so we integrate to find the so-called area. We do it in parts. We go from 0 to 1 because the top function changes. Here this function is the top from 0 to 1, but then from 1 to 2 this equation becomes the top function. So I have the integral from 0 to 1, and the function up top there would be y equal to x. So this is x, and the function on the bottom is the line y equals 0, so minus 0 dx, and then plus I integrate from 1 to 2, and the top function is 2 minus x minus the bottom, the 0 function, dx. And so in calculating this area, we have the integral from 0 to 1 x dx
plus the integral from 1 to 2 of 2 minus x dx. So the area is 1/2 x squared, integrate that from 0 to 1, plus 2x minus x squared over 2, and that's integrated from 1 to 2. You plug in these values, we have 1/2 minus 0 plus 4 minus 4 divided by the 2, we get 2, and then minus 2 plus 1/2, and that comes out to give us the area is equal to 1. Well, let's look at some problems now in 7.2. Let's take 11b. We're given y equal to the square root of x, y equal to 0, x equal to 4. I'm going to rotate this guy about the line y equal to well, it's the x-axis, the y-axis, excuse me. Rotate this about the y-axis. So if we graph this out, we have y equal to the square root of x, it's this guy, and then this goes out to x equal to 4. So this is 4. And then you want to rotate this about the so-called y-axis. The radius here for the so-called disk method is perpendicular to the axis of revolution. You know, this entire graph, if you graph it out to get the shape, is just some cylinder, right? So let's find the so-called radius. We have, this is the open hole, and then we have the big radius here. Notice that the thickness of these radius is with respect to y. So we say delta y thickness. So we're going to call this guy right here big R, and it's big R of y, and then this is the little radius, little r of y. Now the big radius, capital R of y, is just equal to 4. Now the little radius, we have to work on that. Notice that I'm given y equal to x squared, but everything has to be solved in terms of the radius thickness, delta y. So if I have y equal to the square root of x, then that implies that y squared is equal to x. So little r of y, it's just the curve. You get the curve here, right? You get that curve. The curve is given by here, y squared. So now we simply solve. Notice that based on the thickness, that's how I get my limits of integration. So I'm going from y equal to 0 up to this point, but this point corresponds to when x is equal to 4. So if x equal to 4, so I have y is equal to the square root of 4, I get y is equal to 2. So I'm going from y equal to 0 to y equal to 2, and I'm putting the 0 there like a dum-dum. Okay, erase that out, put what it should be, y equal to 2. So now the volume that I calculate based on the formula for the disk method, and this is the washer method, you know, because we have an open space. This is open, right? This is an open shell. integrate from 0 to 2. It is the washer method, the big radius. To be squared minus the little radius squared dy. So I have pi times the integral from 0 to 2. The big radius we said was 4. So this is 4 squared minus the little radius, which is y squared. That guy is squared dy. So we integrate here. We have pi times, to simplify that some more, 0 to 2. This is 16 minus y to the 4 dy. So we get pi times 16y minus 1/5 y to the 5th, evaluated from 0 to 2, and you plug all that information in there and you get 128 pi all over 5. Let's look at part C of that. Here we have y equal to the square root of x, y equal to 0, x equal to 4. Now this time about the line x equal to 4. So we have the graph y equal to the square root of x, and then here we're going out to x equal to 4, and we're going to rotate it about this line as well. And if x equal to 4, then this implies that y is equal to 2, just based on the square root of 4 is 2. And for this guy, notice that I only have one radius. So this is just r of y. And this guy is equal to 4, because I'm going out to 4, minus the curve. The curve is given in terms of y squared. Again, why is it y squared?
The thickness here is delta y, so everything is in terms of y. So you take this equation again and reverse it. You solve for x in terms of y, you get y squared equal to x. So now volume, you have pi times the integral from 0 to 2. Here I have 4 minus y squared, all to be squared, dy. This is pi times the integral from 0 to 2. Simplify all of that. To FOIL that out, 16 minus 8y squared plus y to the 4th dy. This is pi. Now we integrate, we get 16y minus 8/3 y to the 3rd, and then plus 1/5 y to the 5th. Evaluate that from 0 to 2, plug in all those numbers, so we get 32 minus 8/3 times 2 to the 3rd, that's 8, plus 2 to the 5th, 32 over 5. And then at 0, then all those terms are 0. So we have pi, simplify that, 32 minus 64 over 3 plus 32 over 5. And I just pulled out a 32, pi times 1 minus 2/3 plus 1/5. This is the way you do it when you don't have a calculator. 32 pi times, looks like 15 minus 10
is 10 plus 3 over 15. So that's like 8 times 32, 256 pi all over 15. Okay, now part D. D. Y to the square root of x again. Y equal to 0. X equal to 4. Rotate this about the line. X equal to 6. So we draw this out. Now the curve, it only goes up to x equal to 4. But you want to rotate this about this guy here. Again, the thickness is with respect to delta y. So you get the big radius. It's doing that. This is capital R of y. Well, you go to the line, 6 minus the curve, y squared. And then the whole. You got a hole here. There's something that you don't need. It's the washer method. I don't need this part, so this is little r of y. It's just 6 minus 4, so that's just 2. Right? 6 minus 4 is 2. Again, we're still going from 0 to 2 with y. So the volume is pi times the integral from 0 to 2, and then we use the washer method, so it's the big radius, 6 minus y squared to b squared, minus the little radius, which is 2 to b squared dy, and you work that out. You know, I'm getting kind of tired, you know, so you get 192 pi all over 5. Alright. Now let's see. Number 12. Let's look at that one. And I'll work that one out. How about that? You know, in detail. Number 12, we're given y is equal to 2x squared, y is equal to 0, x equal to 2. Well, let's graph this out first. This is a parabola, and then it goes up to x equal to 2 and y equal to 0. So y equal to 0 is this guy. The curve itself is y equal to 2x squared. And then we have just this line here, x equal to 2. So for this guy, part A, it says rotate this about the y-axis. Let's just draw that out, you know, by itself. So I'm rotating this guy about the y-axis. So again, this was x equal to 2 at the origin, x equal to 0. And when I rotate this about the y-axis, notice that I have the big radius, capital R of y, and then the little radius, the one that you want to delete, because that's just a hole there, right? And this guy is our little r of y. Now, notice that since this is with respect to y, because it's r of y, I have to solve for x in terms of y. So if I have y is equal to
2x squared, then I get y divided by 2 is equal to x squared. And so I have x now is equal to plus or minus the square root of y over 2. And we're just talking about the positive side, so we just take x equal to the square root of y over 2. So if that be the case, let's say, for example, if for here they give you that x is equal to 2. See that? So if x is equal to 2, you solve for y. So y is equal to 2 times 2 squared. So we get 8. So I'm measuring this on the graph from 8, from 0 to 8. Here y equal to 0. So now we're ready to calculate the volume. The volume is pi times the integral from 0 to 8. Now why is it in terms of from 0 to 8? Because the thickness determines the limitations of integration. So the thickness is with respect to y, right? Why is that the case? Look, the thickness is changing with respect to y. See that? That's the thickness, right? It's moving with respect to the y-axis, so that's why that's the case. And so here it is the big radius, r of y. And the r of y, the capital R of y, well that's straightforward. That guy is given just to be 2. So this is 2 squared minus little r of y, and little r of y is just the curve, little r of y, this guy right here, it's just the curve, and that's no more than just the square root of y over 2. So this is minus the square root of y over 2 to be squared, all that dy. So we get pi times the integral from 0 to 8, 4 minus y over 2 dy. We simplify that. Simplify it just in terms of integrating. Let's go ahead and integrate this. So we get 4y minus y squared all over 4, evaluated from 0 to 8. So we get pi times 32 minus 64 divided by 4, 8 squared. 64 divided by 4, 16. Just get 16 pi. Let's look at 12b. Here you want to rotate this guy about the x-axis. Well, let's look at that. We have this y-axis, and before it was given that x was equal to 2. So this is a 2, this is 0. Rotate this about the x-axis. We look at the radius. This radius, the thickness is thickness of delta x. This is capital R of x. Well, R of x is just equal to how the function was given. You remember y is equal to 2x squared. So that's the radius, 2x squared. Integrate that from 0 to 2. So the volume is pi times the integral from 0 to 2. Here's just the radius squared, so I get 2x squared, all to be squared dx. So my volume is pi times the integral from 0 to 2. Simplify that, 4x to the 4th dx. Now we integrate, we get pi times 4/5 x to the 5th. X is evaluated from 0 to 2. You plug in 2 for x,
So we get 32 times the 4. So I have pi times 4 times 32 all over 5. And that gives me 128 pi all over 5. Now we'll go ahead and plug in 12C here. This guy, you want to rotate this about the line y equal to 8. Again, it's the parabola. And notice that if x is equal to 2, well, over there you get it. Y is equal to 8. Because again, you're using y equal to 2x squared. So y is equal to 2 times 2 squared. You get 8. So I'm going to rotate this guy about this line here. So let's check this out. You got 2 radius now. Put the radius in red. I have here the little radius. See, the thickness is with respect to delta x, little r of x. Then the big radius. This guy's going all the way down. So again, the thickness is r of x, right? Or delta x, that is. Capital R, right, of x. Very good. So notice here that the big radius itself is just 8. So here capital R of x is equal to 8. And what about little r of x? Little r of x is going to be 8 minus the curve. 8 minus the curve in terms of x, that's 2x squared. So I can calculate the volume. This is pi times the integral. Well, I'm evaluating this from 0 to 2 because anytime that my thickness is with respect to x, I look at the limits of integration. So we're going from x equal to 0 to x equal to 2. So the washer method, the big radius squared minus the little radius squared. Dx. So we simplify this. The volume is pi times the integral from 0 to 2. Get 64 minus. We've just for all this stuff out, put it in parentheses, so we get 64 minus 32x squared plus 4x to the 4th dx. The volume is pi times the integral from 0 to 2. The 64s minus 64s cancel out, right? And then we negate everything else inside. So we get 32 x squared minus 4x to the 4th dx. Integrate that now. The pi sitting out there. We get 32 over 3 x to the 3rd minus 4/5, and this is x to the 5th. Evaluate that from 0 to 2. And you plug in x equal to 2 and all of that, and I just punched that in on my calculator. I got 896 over 15 times pi. Part D. Here, about, rotate this about the line x equal to 2. Here, this is 8 for y, 0. Rotating this about this line here. So we look at the radius. It's this guy, capital R of y. There's no washer method here. You're not considering what's out there, right? No, 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 no. All you're looking for is what's in here. So this R of y, watch it, this guy is 2 minus the curve. But the curve now in terms of y, because the thickness is delta y. So we were given y equal to 2 times x squared, and this implies that x was equal to the square root of y over 2. So this is 2 minus the square root of y over 2. So my volume, pi, look, the thickness is delta y, so I integrate in terms of y from 0 to 8. And here, it's just the radius squared. So this is 2 minus the square root of y over 2, all to be squared, dy. And then when you work that out, you get 80 pi over 3. So it's just the algebra on that, right? Well, number 13. Y is equal to x squared. Y is equal to 4x minus x squared. Well, let's see what we have. Well, the first guy is just a parabola, and it does that. So y equal to x squared. Now this next guy, let's examine that. Let's set this y equal to 0. This implies that I have 4x minus x squared equal to 0. So I get x times 4 minus x equal to 0. X equal to 0, x equal to 4. So it's a parabola. Since that's a negative in front of the x squared, it's a parabola that's going down. I'm going down. Okay. So x and y. So this guy's doing this. You know, I'm left-handed, so you know, I'm kind of deformed in my left hand. But anyway. This is x equal to 4 right here, and this is x equal to 0, obviously. We put both of the graphs together. To see where they intersect. So the first guy is this part right here. And then from this curve, look, these guys are doing something like this. So you get the moon. You get the moon. What's happening in the moon? And this guy is being rotated about the so-called the x-axis. So let's see. I need to find out where these two graphs intersect. They intersect there and they intersect there. So basically you have one guy doing this and the other guy is doing that. Right? So we're looking at this region in there. So if that be the case, to find out where they intersect, we set the two equations equal. To find the point of intersection, set both equations equal. So that gives us x squared is equal to 4x minus x squared. And then we solve there. We have 2x squared minus 4x equal to 0. Factor of 2x times x minus 2 equal to 0. So I get x equal to 0 and x equal to 2. So this point here is x equal to 2, and this guy right here is x equal to 0. So the radius, this radius guy is doing this, and this is part A. We first consider that. Let's put it on another page. This is 0. This is 2, the x-axis, the y-axis, y-axis. Here's the so-called radius slice. It's in terms of delta x. We're going from 0 to 2. Alright, so just put the radius here in different colors. So I have this guy, which is the little r, and that guy was just x, y equal to x squared. And then you have the big guy, so this guy is being determined by this, and you can come on down with it if you will, that's fine. Capital R of x so the little radius is just x squared, and the big radius, this guy, even though we have all of this, look, it's that original function based on this curve up here. So capital R of x is 4x minus x squared. And these two equations were given in the beginning, right? Basically one on top and the other one's on the bottom. So here the volume is pi times the integral from 0 to 2. I have the so-called big radius, 4x minus x squared to be squared, minus the little radius. This is x squared to be squared. This is the washer method, right? Up under the header of the disk method, dx. And you calculate that and you get what you want. Look at 13.b, and I just want to set that one up for you. here this guy is being rotated about the line y equal to 6. So you got y equal to 6 is there. But then you have, you know, this graph up here. That's right down there. And notice that at this tip, this is 2. And if you plug in, if x is 2, y is 4, it's just the parabola. Y equal to x squared. So you can see the gap that you have in between. I want to measure this guy from this line to that curve, and then this is the whole. This is capital R of x. This guy right here is going to be little r of x. So capital R of x is 6 minus x squared, and little r of x is going to be 6 minus that top function up there, that's parentheses 4x minus x squared. So you calculate the volume here, you get pi times the integral from 0 to 2. It's the big radius squared, 6 minus x squared to be squared, minus the little guy squared. So this is 6 minus 4x plus x squared, all that to be squared, dx. We just set that up, and that's fine. The algebra is what's left there. Let's look at number 15. Y equal to x, y equal to 3, x equal to 0, about the line y equal to 4. We draw this out. We got y equal to x, which is doing that. Then you have y equal to 3. So we get 3 here, and then x equal to 0. So x equal to 0 puts me back on the y-axis. So that's this. The line y equal to 3 is there. X equal to 0 is over here, and then y equal to x. So we got a bounded region. Rotate this about the line y equal to 4. So again, you got this radius, you got this. So this is little r, and this is big R. So little r is just the 4 minus 3, you get 1. And big R is the 4 minus x. So the volume is pi times the integral from, do you see where you're integrating that from? We're integrating from 0 to 3. You say y3, this is in terms of x, the thickness of the radius is with respect to delta x. Well, if y is equal to 3, x is equal to 3 too, because I have this guy. Y is equal to x. So I'm going from 0 to 3. And so here, the big radius is 4 minus x to be squared, minus the little radius, that's just 1 to be squared dx. So we get pi times the integral from 0 to 3. Simplify that, that's 16 minus 8x plus x squared minus 1 dx. Pi times the integral from 0 to 3. 15 minus 8x plus x squared
dx. Integrate, we get 15x minus 4x squared plus 1/3 x to the third. Evaluate that from 0 to 3. So we get pi times 15 times 3 minus 4 times 9 plus 27 divided by 3, which is just 9, and that gives us 45, 18 pi. Okay. Well, that'll do it. Thank you.